A sampling distribution is a graph of a statistic for your sample data. While technically you could choose any statistic to paint a picture, some of the more common ones you'll come across are the mean, the range, the standard deviation of the sample, and the variance of the sample. Up until this point in statistics, you've probably been plotting graphs for a set of numbers. For example, you might have graphed a dataset and found it follows the shape of a normal distribution with a mean score of 100. Where sampling distributions differ is that you aren't working with a single set of numbers. You're dealing with multiple statistics for multiple sets of numbers. While most people can imagine what the graph of a set of numbers looks like, it's much more difficult to imagine what stacks of, say, averages look like. Let's start with the mean. Heights and many other natural phenomena follow a bell curve shape. So if you surveyed everyone in your class, you'll find a few short people, a few tall people, and most people would fall in between. If you had 10 classes of students, you might get averages of 5'9", 5'8", 5'10", and so on. If you graph all of those averages, you may get a graph that looks like a sporkahedron. For other datasets, you might get something that looks flattened, like a uniform distribution. It's very difficult to predict what that graph will look like. But the central limit theorem tells us if you have enough data, the distribution will eventually look like a bell curve. Roughly stated, the central limit theorem tells us if we have a large number of independent, identically distributed variables, the distribution will approximately follow a normal distribution. It doesn't matter what the underlying distribution is. Here's an example of the theory. When you roll a single die, your odds of getting any number are the same. You have a 1 out of 6 chance of rolling a 1, a 1 out of 6 chance of rolling a 2, and so on. The mean for any roll is 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by the number of items in our set, that's 6. That gives us 3.5. If we roll the die once, the results are shown in this first figure. It looks like a uniform distribution. It's very flat. However, as the sample sizes increase to 2 dice, 3 dice, and so on, the sampling distribution of the mean looks more and more like a normal distribution. In fact, this last graph below is centered at a mean of 3.5, which is what we calculated above. This is what the central limit theorem predicts. As the sample size increases, the mean of the sampling distribution of the mean will approach the population mean of mu. You can think of a sampling distribution as a relative frequency distribution with a very large number of samples. I hope you found the video helpful. Please take a moment to subscribe to my channel, and I'll see you in the next video.